cover section 2.7. That'll be due on Friday. So I'll post the actual problems after class. The second exam will cover sections 1.6 to 1.8 and 2.1 to 2.8, and this is going to be on Tuesday next week. Okay, so Tuesday next week, and yeah, same deal as last time. We'll meet here in Collaborate Ultra. You'll turn on your webcams so that we can have a proctored testing environment, and I'll email the exam to you, and then you scan it and put it on Dropbox when you're done. Okay, so last time, did we go over problems in section 2.5 already? I think we did. Last time, oh no, we did not. Yeah, so let's take a look at some problems in section 2.5. So 9 to 33, every third problem. Those are 43, 47, and 50. So, and I assigned to you 42 and 46. So, let's look at number 49. In number 49, it states the following: the monthly cost of driving a car depends on the number of miles driven. Lynn found that in May, her driving cost was $380 for 480 miles. So, cost in May was $380 to drive 480 miles. And in June, her cost was $460. So cost in June was $460 for driving 800 miles. Assume, well, I actually kind of don't like that, but assume there is a linear relationship between the cost of driving a car and the distance driven. So it says assume there is a linear relationship between C, which is the cost, and X equal to the number of miles driven. Right. I mean, in all the problems in this section, we're assuming a linear relationship. And remember, with a linear function, right, the idea of slope and y-intercept take on a sort of more specific role. Right. So if you have a function f of x that is linear, mx plus b, the slope is also called the rate of change. And the y-intercept is also the initial condition, or initial quantity. Initial condition, in other words, the value of f of 0 is b. So initial at the beginning. So with this problem about the car, we're assuming a linear relationship between cost and number of miles driven. Find the linear function c that models the cost of driving X miles in a month. So find part A, find C as a linear function of X. Right? It doesn't have to be, of course. I mean, you know, you have a cost for driving so many miles and another cost for driving so many miles. It doesn't necessarily mean that, you know, the relationship is linear. They're just saying that in this problem the relationship is linear. Just assume it. But what is the, you know, what is the property of a given problem dealing with rates of change that tips you off to a function being linear? The idea that the rate of change is a constant. I mean, with a line, the rate of change, the average rate of change, no matter what interval you look at, it's always the same. It's just the slope of the line. And linear functions are the only functions that do that. Right? So whenever you have a problem whose rate of change is, you know, where the rate of change in the problem is constant, you know you're dealing with linear functions. All right, so find C as a linear function of x. How would we do this one? Given this data, how would you find C as a linear function of x? Well, because C is linear, it's going to be mx plus b, where m is the rate of change and, you know, b is the initial quantity, or m is the slope and b is the y-intercept. How are we going to find these numbers given these 2 points here? I mean, 2 points are enough to define a line. So we should have enough info here. Now, how are we going to find that those numbers? Well, if we think of m as a slope, how would you find it? All right, since you've got these 2 points on the line, guys, all right, m is equal to, all right, the slope, which is rise over run, which is what, in this case, given these numbers up here?
380 over 480.
Well, these are the cost values. These are the C values. These are the X values.
380 over 460 and 480 over 800 then?
Well, it's the rise, which is the change in y. Well, change along the y-axis over the change on the x-axis. All right, so in this case, change in y would be 460 minus 380 over change in x, 800 minus 480. Taking care to make sure we did the subtraction in the same order both times. So June minus May over June minus May, or May minus June over May minus June. So this is 800 over 320, so 80 over 32. How does this reduce? So divided by 4, divided by 8.
That can't be 800, right?
What's that? Oh,
That can't be 800.
can't be 800, can it? How did I get that? 80 over 320. Yeah, 80 over 320. So that's 8 over 32. And then 8 goes into 32 4 times. So 1/4. So that's the M. Okay, so far, C of x is equal to 1/4 x plus b. Now, how would we find the b? What might we do to find the b? Right. Well, again, we know that the cost for driving 480 miles is $380, or the cost for driving 800 miles is $460. Right. So we know that the cost for driving 800 miles was $460. Right, so putting this information in here, $460, which is the total cost for driving 800 miles, gives us this equation. $460 is the cost for driving 800 miles. And we know the cost is a linear function, 1/4 x plus b. So we get this equation for b. So 460 is 200 plus b, so 260 is b. So therefore, the cost in dollars for driving the car x miles is 1/4 x plus 260. All right, so you've got this initial cost of 260. So apparently that's the not mortgage. What do you call it? The loan payment. You know, like that's your loan payment or something like that. Your lease payment, $260, and then 25 cents a mile after that, which is, I think, an underestimate. Making sure we got that right. Let's see, 260 plus 480. 480 over 4 is 60. No, 480 over 4 is 120. So 120 plus 260. Yeah, that's correct. All right, part B. Draw the graph of C. What is the slope of this line? Slope is 1 over 4. But anyway, the graph of this thing. So here's 260 is the y-intercept, and you've got a slope of 1/4. It should be a little lower, I think. So 260 is here. You've got a slope of 1/4, so it looks something like this. Okay. Now, of course, you don't always have to, on your X and Y axes, mark them off, 1, 2, 3, 4, 5. Because with this one, you certainly can't do that because, you'll never get to 260 on one sheet of paper or however many sheets of paper you'd need. You don't always have to be so strict about that kind of thing. As long as you have the y-intercept labeled, it tells you what you need to know. And then the slope is positive, so it goes uphill. Part C, at what rate does Lynn's cost increase for every mile she drives? So cost per mile is 1/4 of a dollar, which is, of course, 25 cents. Let's see what else we've got in these problems here. So in number 46, let's see, Jacqueline leaves Detroit at 2 p.m. and drives at a constant speed, traveling west. She passes Ann Arbor, 40 miles from Detroit, at 2:50. Find a linear function d that models the distance she has traveled after t minutes. Well, that's not bad. (42, 44). We did one like 44. We did number 42. Let's take a look at 47. So in 47, west of Albuquerque, New Mexico, Route 40 eastbound is straight and makes a steep descent towards the city. So it's going downhill. The highway has a 6% grade. So Route 42 has a 6% grade downhill, which means that the slope is minus 6 over 100. The slope of the road is minus 6 over 100. Driving on this road, you notice from the elevation signs that you've descended a distance of 1,000 feet. Okay, so you notice from elevation signs that you have descended 1,000 feet. What is the change in horizontal distance? What is the corresponding change in horizontal distance? In other words, how many miles did you have to drive to go downhill 1,000 feet? To descend 1,000 feet. All right, so you've got this road, it's sloping downward. And we've gone down 1,000 feet. And we're wondering, what is the corresponding change in the horizontal distance. Let me see if I can draw a better triangle here. So we've gone down 1,000. So the rise or the fall was 1,000. And what is the corresponding run value? So 1,000 feet. So what is the change in x that corresponds to that, where this slope is equal to minus 6 over 100? Couple different ways to figure this out, but you know what do you guys think? How would one go about doing this? All right, this is rise over run. All right, minus 6 over 100. Right, which is the slope or rate of change of a linear function. And we're trying to find the corresponding x value that goes with the y value of negative 1,000 feet downhill.
Can you do the cross multiplication
Sure,
thing?
the ratios have to be the same. The rate of change is constant, right, over any interval. So here we've got this interval of length x, right? And the rate of change that you get for length x over a change in y of 1,000 is the same, minus 6 over 100. So we must have, as you were saying, that minus 6 over 100 is equal to, again, that's rise over run. Here the rise is not, make sure you make it negative. Negative 1,000 over x. All right, make sure we make it negative. So this is the change in y. That's the change in x. So we're just interested in what the change in x is. You can solve this by cross multiplying. Minus 6x is equal to 1,000 times 100. How do you multiply 1,000 times 100, by the way? We covered this, but just so we're clear on it, how do we do it? How do you multiply 1,000 times 100?
You add the zeros?
Sure, you just, add the zeros. I mean, the different ways you can think of it, right? 1,000 is 10 to the third, 100 is 10 squared, so this is 10 to the fifth, right? Which is 100,000. Right, you add the exponents. Or, you just take the number of zeros and add them together, which is essentially doing this. 3 zeros plus 2 zeros is 5 zeros, right? So this is 1, 2, 3, 4, 5, so 100,000. So x is 100,000 over 6, which is what? Where's my phone? So 16,667, rounding off to the nearest mile. Not mile, sorry. Is it feet per mile? Is it how are they? What are the units? The highway grade, which means that it's all in feet. 16,000 feet. Everything is in feet. So 16,667 feet. All right. So section 2.5, oh, that was section 2.5. Section 2.6, we started on last time. Let's move back to that. So we were talking about transformations of functions, or ways of transforming their graphs more specifically. And this is really one of the best ways to graph functions. It gives you the most accurate way of knowing really what a function is about. If you've got a standard function that you really know something about, then when you transform it in various different ways, everything you knew about that original one transfers to the new one. So, for example, one of the basic functions we know is the parabola. Why? We know about lines, and we know about the parabola. And we'll talk about a couple more in this section. So y equals x squared looks like that. Now, if you want to take the graph of this function and shift it up or down so many units, if I wanted to shift it up 1 unit, we just add 1 to the function itself. So y equals x squared plus 1. If we want to shift it down, this is y equals x squared minus 1. More generally, given the black graph, y equals f of x, the red graph, y is equal to f of x plus c, where c is a positive number, you're just shifting the function upward. And you're adding just this constant c to the whole function f of x. Correspondingly, if you want to go downward, you subtract c. Shifting horizontally, okay, it's a little bit different. Starting with the function y equals f of x, when you want to shift to the right, c units, right? What you do is you take the function and replace x with x minus c. So this becomes f of x minus c. C is a positive number, and you're subtracting it, and that shifts it to the right, c units. If you want to go to the left, you add c. And it's kind of the opposite of what you think you would want to do. Okay, but why does it work that way? Well, this function here, you pick a special point. This special point happens at x equal to 0 in this function. Right here it bottoms out at x equal to 0. Well, where is this equal to 0? X minus c is 0 at positive c. Not at negative c, at positive c. X minus c is 0, so this special point from the black graph moves to c. Similarly, x plus c is equal to 0 at x equal to minus c. So this special point for f of x happening at x equal to 0 shifts over here to minus c. So, for example, with the parabola again, y equals x squared. If you want to shift it to the right or to the left, 1 unit, we're not adding 1 or subtracting 1 to x squared. We're adding or subtracting 1 from x. So this is y equals x minus 1 squared, replacing x with x minus 1, which gives you this function, x squared minus 2x plus 1, or adding 1 to x, y equals x plus 1 squared. Now, of course, you can combine these two things. Okay, find the function and its graph, which is obtained from the standard parabola. Let's not do the parabola, the standard function, y equals square root x by shifting down 1 unit and right 2 units. So I'm going to take the function y equals square root x, shift it down, and then to the right by 2 units. Okay, so let's see how that looks. So y equals square root x, it's essentially the parabola laying on its side, but just half of it. Right, y equals square root x, it looks like that. Of course, the square root of 0 is 0. The square root of 1 is 1. And it's the y-axis, that's the x-axis. The square root of 1 is 1. 2, 3, 4. The square root of 4 is, of course, 2. Right? Not quite in the right spot now, is it? Better. Alright, square root of 4 is 2, so on and so forth. So that's the graph y equals square root x. So let's take that graph. And we're going to shift it down 1 unit and then to the right by 2 units. Okay, and these special points that we've identified, they get moved along with it. Okay, so we start here. Now we're going to go down 1 unit. All right, down 1 unit and then shift it to the right 2 units. Oops. So this special point 1, 1. Oops. This special point that was, maybe I should leave it there so that we see it. That was the point 0, 0. This was the point 1, 1. This is the point 2, 4. So that special point 1, 1 goes from here, and then we shift it down 1 unit. So it's going to be right there. And now we're going to shift it to the right by 1, 2 units, like that. So this was 1. This now is 2. And this point right here is 3. And this point was 0, 0. And so this point down here, well, we shifted down 1 and to the right 2. So what's the coordinate of this point down here? Because the 1 is right here more so. What's this point down here? It was 0, 0. Now it went down 1 and then to the right 2. So what's the coordinate of this point here?
2, -1.
2, -1. And what is the algebraic expression that goes with this function? So this was y equals root x. This one is going to be y equals, so we're going to shift down 1. That means we subtract 1 from the function. Right, so if this was y equals f of x, which is the square root of x, this one, the red one, is going to be y equals f of x minus 2, to shift to the right 2, minus 1, to subtract 1. And that happens to be just square root x minus 2 minus 1 on the outside. All right, so this shifting up and down and left and right, you can combine the two together. All right. Other transformations involve stretching or compressing up and down. Well, vertically, I guess. Let's look at a function made up of a couple different lines. So this is y equals f of x. And let's say this point here on the y-axis is equal to 2, and this point here on the y-axis is equal to 1. Forget about the x-coordinates for the moment. Just let's concentrate on the y's. So that's y equals f of x. Now, if I take that function and multiply the whole thing by 2, the whole function by 2, what it ends up doing is stretching that function vertically by 2 units. So it gets stretched upward like that. All right, so that would be the function y equals 2x, or 2f of x. Y equals k f of x for some k bigger than 1. Well, let me put a, no, we'll do that as an example. So it gets stretched upward. Similarly, if you want to sort of squash it vertically, so that's k f of x for x bigger than 1. And now if you want to smush it down, you multiply it by something that is less than 1. So that's y equals f of x. And then if you want to sort of flatten it to half its height, like that, or some other fraction of its height, then you divide by k. So this is y equals 1 over k f of x for 0 less than 1 over k less than 1. And then in this one, yeah, it was k bigger than 1. Okay, so stretching up vertically or squashing down vertically is done by multiplying the function by a constant that's bigger than 1, or by a constant that's less than 1 but still positive. So in this particular picture here, the constants used are, of course, 2 and 1/2. So this is y equals 2 f of x. So this point up here is a 4. This is 1, this is 2. And this point over here is a 2. And then this function down here is y equals 1/2 f of x. All right, you can also stretch and compress horizontally. So there is this famous function called the sine function, which you'll learn about in your trigonometry and pre-calculus class next semester. So if you had a function that looks like this, y equals f of x, and you want to stretch or compress horizontally, well, it's similar to the idea of stretching and compressing vertically, is that you multiply by a positive constant, but this time not outside the function, inside the function. Okay? And it's, again, sort of the opposite of what you would expect. I mean, if you want to make the function bigger, when you want to stretch vertically, you multiply by a constant bigger than 1 on the outside. If you want to compress it or squash it, you multiply by a constant less than 1 on the outside. Here, it's the opposite. To stretch, you multiply by a function by a constant less than 1, and to compress by the constant bigger than 1. So if this is y equals f of x, and let's put actual numbers here, 1, 2, 3, 4, 5, like that. So I'm going to take this function, and I want to squash it by half. So the 5 goes all the way to 5/2, which would be right here, 2.5. So this red function, that is y equals 2f of, f of 2x. So to squash by a half, we multiply the x by 2. To stretch by 2, a factor of 2, make it green. To stretch by a factor of 2, so I want to take the 2 all the way out to, is it even going to fit? The 4, let's try that again. Move this here. Okay, so we can't go by that. Let's say, well, why don't we just make the whole picture smaller? There we go. All right, so then this green function is y equals f of 1/2 x. So to stretch a factor of 2, we multiply the x on the inside of that function by 1/2. Okay, so the points of interest here, this point, the red one, this is 2.5. This was 3. That was 4. This was 5. This was 2. Oops. I actually have things. What did I do? That's supposed to be 0. Ugh, my picture is all off kilter now. Let's try it again. So this is 0, 1, 2, 3, 4. So this point, yeah, I did the wrong stretch. So the 4 gets compressed to the 2. So that's f of 2x, and then this one, the green, starting at 0, so now the 2 goes out to the 4, so it's just that much. Alright, so this one is y equals f of 1/2 x. Alright, so the black function is y equals f of x. The red function is y equals f of 2x. And the green one is y equals f of 1/2 x. This is kind of hard to spot sometimes with functions that we're used to dealing with, but let's take a look at what this can look like with the parabola. So, for example, so here is how this would look with the parabola. So let's do y equals x squared minus 1. So y equals x squared minus 1. Looks like this. It has x-intercepts at 1 and -1. So this is y-intercept at 1 and x-intercept at 1 and -1. So now if I want to stretch it horizontally by a factor of 2, so these points that we're at, 1 and -1, they need to move to 2 and -2. So did that do it? Now I need to stretch it a little more. So that's 2 and -2. These right here are 1 and -1. And then that's still the point, 0, -1. So we multiply, so this is y equals x squared minus 1. So we multiply not the function by a half, but the x by a half. So this is y equals 1/2 x squared minus 1. So this turns out to be y equals x squared over 4 minus 1. Similarly, if you multiply the x by a 2, okay, then it's going to compress it by a factor of 2. So that would take this function here, let's make it a different color. All right, and compress it like so. So I can't quite get it. Yeah. Y equals x squared minus 1. Now the blue function is y equals 2x squared minus 1, which is 4x squared minus 1. And the x-intercepts that were at 1 and -1 are now at a half and -1/2. So to compress by a factor of 2, you multiply the x by 2. And to stretch by a factor of 2, you multiply the x by a half. So it's the opposite of what you think it might be. So the horizontal transformations, shifting and stretching and compressing, are the opposite. To shift right, you subtract a positive number. To stretch out, you divide by a positive number. Right? Whereas the vertical transformation is not the opposite. It is what you think it should be. Right? To stretch upward by a factor of 2, you multiply the whole function by 2. To shift upward by 2 units, you add 2 to the entire function. All right. A couple other transformations. The reflections. So if you've got a function y equals f of x, so let's make just function like this, y equals f of x. if we take that function and we want to flip it upside down, so reflect it along a horizontal line like that. That is accomplished by negating the entire function. So this is y equals minus f of x. This is the reflection of f of x about the x-axis. So it leaves the x-coordinates the same, and it just takes the y-coordinates and negates them. So the geometric effect of that is to reflect it around the x-axis. Again, that's the x-axis, that's the y-axis. If you negate x itself, then you flip it around the x-axis. So this is f of negative x. Y equals f of minus x. It is the reflection about the y-axis. And then sometimes we like to do the reflection about the origin. So we reflect around the x-axis and the y-axis. So you negate the whole function and you negate the x. So let's just erase this one. So now I'm going to take this and I'm going to reflect it. Where did that go? I'm going to reflect it along a horizontal line, along the x-axis, and also I'm going to do the reflection along the y-axis, like that. And that's called a reflection through the origin. Y equals minus f of minus x, the reflection through the origin, right, or the reflection about both axes. Now, some functions, they don't change when you do that sort of thing. If I took this function here, oops. This function here, this is actually the graph y equals x to the third. If you were to reflect it around the origin, you would get the same function back. The reflection through the origin is the same function back again. So if you started with the function f of x equals x to the third, then minus f of minus x, it's 1056, is minus x to the third. Minus x to the third is minus x times minus x times minus x. 4 negatives make a positive, and you get x to the third. Right? So if I were to do that reflection through the origin, I would just take the function and put it back. Right? It gives me the same exact function back. Such a function is called odd. Not a great term, but there it is. That is when f of x is minus f of minus x. That's called an odd function. And y equals x to the third is one of the standard examples. And then that sine function that we talked about before, that's also an odd function. Okay, so tomorrow we'll discuss section 2.6, move on to 2.7. Don't forget about the assignment that's due tonight. Email me with any questions or concerns, okay?